So this is going to be a video on topic 4.6, Newton's law of universal gravitation. So the do not question says, well, if the sun suddenly vanished from existence, do you think the Earth would instantly stop orbiting where the sun used to be, right, and go in a straight line and no longer orbit uh, the sun in its elliptical path? Or do you think it would take time, right, for Earth to kind of realize, well, the sun is not there anymore, and I'm gonna stop orbiting how I usually orbit, right? So would it take time for the Earth to realize that the sun just instantly disappeared, right? And so if I take time, we're not talking about infinite amount of time. We're talking about maybe 8 minutes, maybe the amount of time a light takes to reach the Earth, right? And so this dude now question talks about, well, two different ideas of thinking of about gravity. And so the first one of these ideas is how Newton thought of gravity, and the other idea is how Einstein thought gravity worked. And ultimately, Einstein was correct. Einstein was correct about how gravity worked, but well, then the answer to that question is yes, it would take time for Earth to realize that, well, the sun is no longer there, right? 8 minutes and 20 seconds to be exact, which is the amount of time light takes to reach the Earth from the sun. So it takes that much time, right? Because gravity is a wave, right? And gravity travels at the speed of light. So Earth wouldn't realize that Earth would definitely take time, right, to suddenly stop orbiting. All right. In this video right here, you guys can watch on your own. It's a pretty good representation of how gravity works. I highly suggest you do watch this video. It's 7 minutes long. I'm not going to show it because, well, I'm going to get copyright striked, right? So Newton came up with this law, right? And he posited, well, every two masses anywhere in the universe have are attracted to one another, right? They exhibit this gravitational force of attraction, right? And so, well, and this is the formula for that. So two masses are attracted to each other based on the distance and something we call the gravitational constant, G, right? So the formula is Fg, your force due to gravity, force of attraction, G, m1, mass 1, m2, mass 2, over r squared, right? And what if I told you that, well, everything, hold on, right? So any two masses in the universe, right? Like that, for example, the chair you're sitting on right now, well, you're attracted to that chair, right? You exhibit a force due to gravity on that chair that you're sitting on. And the chair does the same exact thing. The chair also exhibits a force due to gravity back onto you, right? Your pencil has a force due to gravity, and you are attracted to that pencil, and that pencil is also attracted to you, right? You also have a force due to gravity. Well, and that's what Newton said, and that is actually correct. Well, how do we make sense of it, right? Let's actually not have the value in there. So how does that make sense, right? How does that make sense? Well, think about it. Well, what's the difference between the pencil and the Earth? Well, the biggest difference is that the pencil is clearly has a lot less mass, right? And the Earth has a much greater mass, and so it exhibits you feel the force due to gravity from Earth. Whereas from the pencil, you don't really feel all that much, right? Because the pencil doesn't have much mass. And if you think about it, it takes, let's have actually two masses that are 100 kg, right? Which is kind of around 100 water bottles. And you can clearly see that, well, my force due to attraction is in the order of 10 to the negative 8 newtons. 10 to the negative 8 newtons. The Earth exhibits a force due to gravity of 1,000 newtons on you, and that's assuming we're on the surface of the Earth, right? Because we're clearly very far away from the Earth. Oh, Earth center, right? And so the Earth exhibits somewhere around 1,000 newtons on us, right? And that's a force of attraction. But the masses with 100 kg don't really exert all too much of a force through gravity, even though they're extremely close to one another. And you can see that, well, as we get closer, our force due to gravity increases, but you went from an order of 10 to the negative 8 newtons to 10 to the negative 7. That's extremely small, right? That's extremely small. And so you don't really feel this force due to gravity, this force of attraction, because the masses have so little mass that you don't feel anything, right? Anything substantial, at least. And so let's actually move on to a practice question, right? And so obviously you're going to do this. So 2A. So we're going to identify our knowns, right? So we have two 40 kilogram spheres. So we have mass 1 is equal to 40 kg. Then we have mass 2 is also 40 kg, right? So we have two masses are separated by a distance of 10 meters. 10 meters. Let's actually change color. Actually, that's not. And the question is asking, well, what is the magnitude of the gravity? We're looking for force due to gravity. And our force due to gravity formula is equal to G m1 m2 r squared. And so G is a gravitational constant. It's in your notes. So G is always equal to 6.67 times 10 to the negative 11 Newton meter square over kg squared. Right, and so you have 6.67 times 10 to the negative 11, 40 times 40 over r squared, right? And r squared is 10 squared. And so you plug this into a calculator. Let's plug this into a Google calculator. Let's plug this into Google calculator. Google calculator. So now we have 6.67 times 10 to the negative 11. And oh, we don't need that. Times 40 times 40. Well, we don't want to do that yet. So let's put that in parentheses and divide it by 10. Let's actually also put this in parentheses. 10 squared. All right. And so we have this number right here. The E signifies exponent. So we do have, and it comes out to 1.07 times 10 to the negative, was that negative 7? Pretty sure it was negative 7. Negative 7 newtons. And so that's the force due to gravity of two 40 kilogram objects that are 10 meters apart from each other. Barely anything. Actually, it's 10 to the negative 9. My bad. So it's 10 to the negative 9. 10 to the negative 9. Right. And that's a practice question right there. Move on to the second one, right? And so you're basically doing the same exact thing. You have 2 kilogram soccer balls, so mass 1 is 2 kg. Mass 2 is also 2 kg, and the distance between the centers is 0.2 meters. And so you're also looking for the gravitational force of attraction. So you're looking for Fg. And so you're going to do the same exact formula again. Do the same exact formula again. And so you have r squared. So 6.67 times 10 to the negative 11. You have two masses, right? 2 times 2, r squared is 0.2 squared. And then you just plug this into a calculator. Right, so let's do times 2 times 2 0.2 squared. And then you get 6.67 times 10 to the negative 9. 6.67 times 10 to the negative 9 newtons. Alright, and it's essentially the same thing. And so practice problem 2C also follows the same exact logic. Alright, it follows the same exact logic. And then we move on to 3A. 3A, and so the mass of both objects are doubled. And there's a very specific way to solve this, right? Because this is a proportion question. It's a proportion question, and you might have learned this in math. So what happens to the force of attraction between two objects if you double the mass of each object? Well, think about it this way. We have this formula over here. We have this formula over here, m1, m2 over r squared. Well, if we double both of our masses, well, our formula then becomes g 2m1 hold on, 2m2. Actually, we don't need a parentheses there. 2m2 over r squared. And if we simplify this, right, we have 2 times 2, right? So that's where these two come together. You have 2 times 2, well, then your equation, your formula becomes 4g m1 m2 over r squared. And so compared to your original equation, if you double both your masses, well, your final equation is 4 times. Your final equation is 4 times your original equation. And so what happens if you double both your masses? Well, if you double both your masses, well, then you quadruple your force due to attraction. And the same thing goes for the next question, right? So the next question follows the same exact logic. And so if you double both your if your masses are quadruple this time, right? So if you quadruple your masses, and so if you quadruple your masses, your equation becomes g 4m1 4m2, right? You're quadrupling your masses, and so 4 times 4 gives you 16g m1 m2 over r squared, right? And so that's 16. So that's gonna increase your force due to gravity by 16. Okay, cool. End this video.